Hello guys, welcome to Rocket Tutorial 1. Okay, so in this tutorial we are going to see how to design an model rocket, or you can say the high power rockets. Okay, so we can start with some basic things. Okay, we are not going to in advanced level in the very first video. First of all, I am going to introduce that I used an open rocket software app for the best designing and manufacturing. Okay, so opening this app. First of all, I am going to introduce this app for you. You can see here that it is an board area in which the design will appear here, or you can say that we can design our rocket in this portion. Okay, you can see your view type in this video. You can see that top view, side view, back view, or etc. Okay, I choose side view. Okay, then after you can see here that it is flight configuration. In flight configuration you have to establish, or you can create a motor. Okay, there is an stability, center of gravity, and center of pressure. What is center of gravity and center of pressure, we can explain you after the video. Means um, first try to understand the components of rocket, inner components, outer components. Okay, then after we are going to center of gravity and center of pressure. Okay, you can see here that it is an apogee. Okay, apogee stands for the highest altitude gained by the rocket, is called an apogee. Okay, now start designing. Okay, you can see here that it is a sustainer. Okay, so what is sustainer? Sustainer means it is the parts, or you can say the components of the rocket. Okay, it consists of nose cone, body tube, transition, fins, launch lug. Okay, it is the parts of the rocket. Okay, first try to start with a nose cone. When you click on nose cone, the table will appear here. It indicates that if you want to buy directly from an industry, you can buy it. Okay, but we are going to manufacture in our uh, so that we can go for this. Just close. You can see here that it is a nose cone shape. Okay, so nose cone shape, there is an ogive shape. We cannot take an conical shape or any other shape. Why? Because in conical shape you can see here that it is an less aerodynamic drag. Okay, that is a less aerodynamic drag here. And after nose cone, the body tube is there. Okay, so body tube sense there is an high pressure. Okay, inside the body tube. Okay, then aerodynamic drag is less here, and the body tube sends high pressure. Okay, so we cannot take an conical shape, we can take an ogive shape. Why? Because in ogive shape uh, the shape parameter is 1. Okay, and then after you can see here that the aerodynamic drag is less here, and then after body tube sends that is in less pressure. Okay, so which is good. Okay, so we can take an ogive shape. You can see that the shape parameter is 1. Why we can take shape parameter is 1? When if you take the shape parameter goes to 0 downward, then it seems like an conical shape. Okay, so we cannot take shape parameter 0. You can take the length of your own side like 15 centimeter, but I prefer it is a 20 centimeter. Okay, then after base diameter, I choose the base diameter of approximately 6 centimeter. Okay, then after the wall thickness is going to be 0.2 centimeter. Okay, and when you can see here that it is a field. Okay, what it indicates that, let's understand this by 3D unfinished to you. Okay, you can see here that it is our nose cone. Okay, when you click on field, the inner portion is filled. Okay, you can see here that it is filled. Then why fill is when fill is used, if you have the problem in center of gravity. Okay, and therefore you have to use field. Okay, but first of all we are understand the center of gravity and center of pressure. We cannot use field. Okay, then the material. Okay, so material is most important part of the rocket, which material you are going to use. Okay, for nose cone we are going to use basswood. Okay, basswood is good, or you can also take a balsa wood, but I preferred basswood is good. Okay, and there is a regular paint of component finish. Then after you can go for solder. Okay, so let's understand solder. uh Solder is generally, you can say, the basic that it is an extended portion of nose cone. Okay, it works like a coupler. Okay, which joining the nose cone and body tube. Okay, why coupler is used when you have to joining the body tube. Okay, joining two body tube is called coupler. But in shoulder you have to join nose cone and body tube. Okay, it is called shoulder. Then after, first of all, we are going to decide the length of our shoulder. We can go for uh 3 centimeter, or you can also take 4 centimeter. Okay, but I choose 4 centimeter. First go to side view. Okay, you can see here that we can go for the length of 4 centimeter, and the diameter is, we can take as less than 6 centimeter. I take 5.4 centimeter is the length, or you can also take 5.6 centimeter. Okay, then after you can go for that thickness. Okay, our thickness is same as per the nose cone, which is 0.2 centimeter. Okay, then if you want to use end cap, you can use. Okay, then after, first of all, I don't tell you why nose cone is used. Okay, so the function of nose cone is to reduce the aerodynamic drag of an rocket. Okay, and helps to increase the velocity of rocket. It is the function of nose cone. Then after, we are going to use an override. Okay, why when you have problem in the center of gravity, you can input some mass here. Okay, then after you have to click on override mass, then you have to increase your mass as per your need. Okay, just click cancel because we don't have any problem in mass here till now. Okay, and we are going for appearance. Okay, uh, if you think that our logo is printed in our rocket, so you can go for use default color and changing the color of your line like green as per your need. Okay, then after, you have, if you want to use the sticker inside, then go for this. Select the file from your computer or and laptop. Okay, I use default color for that. Now go on comment. Okay, so comment is not compulsory. If you want to add some comment like nose cone is made, nose cone is made made up of basswood. Okay, so you can like that, but it is not compulsory. Okay, now click on okay. Now the other another our nose cone is done. You can see here that it is our nose cone. We can see this nose cone in our back view also. You can see it is a back view. Okay, in top view you can top view and side view is same. Okay, now go for 3D figure. In 3D figure, our nose cone is seems like this. Then after 3D finish, you can go for this. You can see here, and for 3D finish, it is same. Okay, now let's come to side view back. Okay, uh, now we have to use an body tube for uh so what is body tube? Okay, so body tube is an airframe which consists of payload system, you can say avionic system, rock or recovery system. Okay, but in this video we are not going to use any payload system or avionic system. We are only going to use an recovery system for this. Okay, you can take the length of your own choice. I prefer 75 to 80 70. Sorry, I will take, let's take it 75 centimeter. Okay, the three times of nose cone. Okay, then the outer diameter is same as 6 centimeter. Why? Because the outer diameter of nose cone is equal to the outer diameter of body tube. Okay, then the inner diameter. Okay, so inner diameter is also an automatic. Why it is 5.6? Because the outer diameter of shoulder is equal to the inner diameter of body tube. Okay, then after the wall thickness is same as 0.2. Okay, if you can fill it. Now material, you can take the material as per your need, but I choose PVC pipe is good for this. And then after going to use and mortar, okay, this component is not on mortar mount, okay, so we cannot click on this. As per I told you, override apprehension comment you can use. Now click on OK. Now the another thing we have to add is an inner tube. Okay, so go for inner tube. Okay, what is inner tube? Inner tube, the function of inner tube in this is it is an motor mount, okay, in which the motor is used. Now we can say see the dimensions of inner tube, like the length we have to taken is you can taken as 25 centimeter. Okay, and then after the outer diameter you can taken as 4 centimeter, or you can take 5 centimeter also. Okay, or we can take the less than 5 centimeter. Let's take it 4.5 centimeter. Now the inner diameter is 4.9 centimeter. Now it is become 4.4 centimeter, and the wall thickness is 0.05 centimeter. Now you can see here that placement, okay, position relative to bottom of the parent component, which indicates that our body tube is our parent component. Okay, then plus 0 centimeter indicates that it was in the same phase. Okay, if you're going to reduce the phase to -1, it seems to backward. Okay, now taken as the relative position at 0 centimeter. Okay, now the material, okay, we can use the material here cardboard, we can use cardboard. Now the motor. Okay, so this component is a motor mount, so click on right click and the motor overhang. Okay, motor overhang means that when you at which position you have to put. Okay, so we are going to put motor at 0 centimeter. And the ignition, okay, ignition at which you can see that it is a symbol. This parameter can be override in each flight configuration. Okay, the current design has only one stage. Stage can be added by clicking new stage. Okay, but go for this. Don't go for this. You can see here that it is an automatic launch or ejection charge. Okay, when you burn the motor, it automatic eject. Means uh, the ejection start flowing without any delay. Okay, now cluster, why cluster, if you want to use any more than one motor, you can go for an cluster. Okay, same as when you go for two motor, you have to decide the radial position, but I choose single motor cluster. Again the same, if you want to go for override appearance comment, now click on OK. Now we are going to use an centering. Okay, so the function of centering is to hold the body tube and inner tube. Okay, um our inner tube consists in the center line, uh that for centering is used. Okay, that's why centering is used. So we have to uh make centering in body tube. So click on centering, and just it is an out it is, you have to click on automatic. Now go for an placement. Okay, the placement is from this side. Okay, you can see here that the outer diameter is 5.6 centimeter. Okay, so how it comes, it comes that the inner diameter of body tube is outer diameter of centering. Okay, then the outer diameter of inner tube. Okay, outer diameter of inner tube is the inner diameter of centering. Okay, then after material, you can go for material as cardboard, same, and then click on OK. Now another, we have to put three centerings. Okay, now click on centering, just change the relative position. I take the relative position uh, minus 16 centimeter. Okay, let's take 16 centimeter. Now we are going to use only one more center ring wrong and just take little back. Okay, minus 4 centimeter, which is good. Now click on OK. Now the another this is the last component we are going to add. It is an fins. Okay, fins are added to the body tube. Okay, so go for elliptical fins. I prefer an elliptical fins more because elliptical fins provide the stability of an rocket. Okay, that's why elliptical fins are more used. We are going to use the number of fins 3 to 4. Okay, because 3 fins are more difficult to three fins are more difficult to use, and if the fins are increased, so the stability also increase. Okay, that's why the fins I am going to take the 4 fins. Okay, the fin can so the function of fin can and fin rotation is used when if you want to spin out your rocket. Okay, then after root chord. Okay, so root chord means the distance between this you can see the distance, and you can say the length of your fins. Okay, I prefer the length taken as 13 centimeter. Okay, then after taken the height is approximately 5 centimeter, or you can take an as 6 centimeter. Okay, now see, it is good. Now the you can see the fin cross section area. We can take a fin cross section area as per your need. I choose square. Then after the thickness is same 0.3 centimeter. Now the placement. Okay, so placement position relative to the body of the parent component. Okay, body of bottom of the here the parent component is always our body tube. Okay, then plus 0 centimeter indicates the relative position. If you taken as a little bit backward, minus 1 centimeter, you can use the material here like plywood. Okay, I preferred plywood for this, and the component finish is always regular paint. Now we are going to just leave root fillet. Okay, we are going to see root fillet in the very next lecture. And fin tab. Okay, so in fin tab we can see that the tab length, just click on calculate automatic. Okay, so it calculate automatics. You can see here that the tab length is 9.8 centimeter. Okay, this the square you can see it is the length of 9.8 centimeter, and the height is approximate not approximately, it is equal to 0.75 centimeter. And the tab position, okay, the tab position is minus 1.6 centimeter. Okay, so it is from here it is minus 1.6 centimeter. Now relative to the not middle of the parent component, you can take at the bottom of the parent component. Okay, now it is okay, 3 point minus 3.2 centimeter. Okay, which indicates from the body tube it is backwarded to minus 3.2 centimeter. Okay, now just click on okay. Now our designing is ready, but the thing we are going to add is motor configuration. Okay, so choosing a motor is very difficult and very you have to choose this type of motor which has high impulse and which is safe. Okay, safe for flight. So go on motor configuration. Now you can see here that the motor mount. Okay, so I told you that inner tube work as motor mount. Okay, so inner tube, and go for new configuration. And then after you can see here that it is a manufacturer. I preferred Aerotech industry, which going to use the great and high safety motors. Okay, you can see here that the total impulse is a to 0. Okay, motor dimensions, you can see here that it is a dimension of our inner tube, which is 44 mm and 250 mm. Okay, so taken as 232 mm, and the total impulse is 487, diameter 38, you can see here that it is a case which indicates the serial number, and then after it is a model which is I59WN. Okay, just click on it and go for okay. Now it is okay that the you can see here that our motor is established, but there is a difference, okay, which what our stability is not good. Okay, to increase the stability, what we have to do, I now coming from main point, our center of gravity is front, and the center of pressure is after. Okay, when the distance between center of gravity and center of pressure increases, you can see you can tell that our rocket is more stable. Okay, for increased stability, what we have to do, just go for rocket design, nose cone, edit, and click on field. Okay, now it is okay. If you go for shoulder, just click on and keep. Okay, so it little bit increases. Now click on okay. uh, Now the another thing we are going to see, that just decrease the uh, length or height of the fins. I decreased from 12 centimeter to 11 centimeter. Okay, and the tab height, sorry, the height is going to be 5 centimeter. Okay, or you can, no, the height is equal 6 centimeter, and go for fin tab and click calculate automatic. Now go on okay. So you can see here that our stability is 1.45 calories to 9.18 percentage. Okay, now if you want that our center the distance between center of gravity and center of pressure increases, so what you have to do, just go on motor mount, modern configuration. You can see here, sorry, uh this. Okay, so the dimension we have to just know, select motor. You can see here that diameter is 38 mm, and we are not going to change the diameter but change the length of inner tube. Okay, so 232 we are going to taken as the length of inner tube is 230, taken as 230, 233. Okay, now click on okay. Sorry, my mistake. 230, 23. Now it is okay. No, it is difficulty, so I taken as 24, sorry, 24. Okay, 24 centimeter. Now it is okay. Now the another thing we are going to use, that the change the material of nose cone. Okay, so I choose the basswood, so you can also take an fiberglass. Okay, you can take a fiberglass, which is good. Or the another thing, you if you want to add, uh, just go PVC. PVC is also good, so let's take on PVC. Okay, now click on OK. So you can see here that our stability is increased to 3.19 calories and 20.2 percentage. Okay, so the distance between center of gravity and center of pressure also increases. Okay, so now we can say that the our rocket is stable. Okay, so let's add recovery system. So recovery system consists of parachute and shock cord. Okay, so we are going to first put shock cord. Okay, now material is elastic cord. Take length of shock cord is more. Let's take taken as 70 centimeter. Okay, 70 centimeter. Now position top of the parent component and just reduce it to little backward. Just click on automatic and now increase the pack length. Okay, so our pack length is increased. Now click on OK. Now another recovery system which is parachute. Okay, just click on parachute. Then after canopy, canopy means the parachute. Okay, so just taken the diameter is equal to 35 centimeter, sorry, 35 centimeter, and the material is ripstone nylon, which is good. You can also take silk. Okay, drag coefficient is CD, which is equal to 0.800. Shroud lines. Okay, so shroud lines you can decrease or increase. Okay, so I decrease the shroud lines. Line length is take much greater. Let's take on as 40 centimeter, and the material you can use elastic cord or any other another material like elastic rubber band. Okay, now just go for placement. In placement you can see at the top of the parent component. Okay, little backward, go for this. Just click on automatic, and then after you can see that just increase the pack length. Okay, now just okay, now it is okay. You can see here the deployment. Okay, so deployment means when your motor burns out, when the rocket gains the highest altitude. Okay, when going for highest altitude, the parachute will eject. Okay, so it tells that the first ejection charge of this state. Now click on OK. Now our rocket designing and rocket is ready. Okay, so just see the flight simulation. Okay, you can see here that the length of our rocket is 95 centimeter. Okay, so the full length is 95 centimeter. The diameter the highest diameter is 6 centimeter. Mass with no motor 896 gram, and mass with motors is uh 1 kg and 383 gram. Okay, so generally the model rocket is made up of 1.5 kg, so which is good for us. Then after apogee means 1752 meter. Just see on the feet, so you can go for feet also. So 1572 means 5157 feet it goes. Okay, which is good. Now you can see the maximum velocity of the rocket, which is 165 meter per second, and the maximum acceleration is 115 meter per second square. Now you can go for flight simulation. In flight simulation, first you have to go for run simulation, and then after you can see here that simulation 1. If you change the name, you can change the name by one by yourself. Okay, but I prefer not to change the name. Okay, if you want to see the graph of your rocket, you can also graph. Let's see that the graph of motor ignition, motor burnout, apogee, and ground heat. Okay, so now go for plot. You can see here that our graph is vertical motion. You can see here at this altitude, it is the highest apogee. Our rocket gains the highest altitude, and then after at this time you can see at this time at this point our motor will burn out, and after motor burnout it gains total this type of this distance. Okay, then after motor ignition at 0. Okay, and you can see that uh, it is the point. Okay, let's take on as 8.5 or 9. Okay, at this point our motor will burn out. Okay, you can see the our motor burn out in this. Okay, you can see that it is our name of our motor, velocity of rod, which is equal to 14.6 meter per second. Then after apogee you can take an as 1754 meter. Then after velocity at deployment. Okay, at deployment there is no velocity. How it is possible?